Hi, this is Bob Pryor, and today we're talking about verifying trigonometric identities. Let's review what we already know. We have the reciprocal identities, which can be written forward or backward. We know that because secant and cosine are reciprocals, that secant theta is 1 over cosine theta, but that also means 1 over cosine theta equals secant theta. And you should by now be familiar with all of the other reciprocal identities. We have the ratio identities. Tangent is sine over cosine and cotangent is cosine over sine. Did you notice that cotangent is cosine over sine? That might help you memorize these better. Tangent, not a cofunction, has sine, also not a cofunction, in its numerator. Of course, we have the all-important, all-powerful Pythagorean identities. We have the most basic of Pythagorean identities, on which all others are built, including the cosine squared theta, which is equal to 1 minus sine squared. Memorize these forward and backward. We also have Pythagorean identities that include tangent and secant. That was the basic divided by cosine squared, and the cotangent cosecant. All right, so let's talk about proving or verifying identities. The identities we're going to talk about look like equations. I mean, we saw already cosine squared plus sine squared equals 1. That's an equation. That's the kind of identities that we're going to be looking at. But we're going to be seeing other ones now, and our job is to prove or verify the identity. And since it's not yet proved, we're actually going to call it a supposed identity. In other words, we're going to be given this equation and told it's an identity. We're to prove that it's an identity, and maybe it isn't. So we're going to use our skills to prove that it's true. However, we cannot assume that the left and right sides are equivalent. So we're not allowed to treat the identity like an equation. We can't do the same thing from one side as we do to the other. Instead, we have to kind of keep it all separate. We can't just say multiply each side by the same number, or take the square root of each side, or add the same terms to each side of the equal sign. Can't do that in these supposed identities. Instead, our job is to manipulate, simplify only one side of this supposed identity and make it identical to the other side. So once that task has been complete, the identity has been verified or proven or demonstrated. Now, once an identity has been proven, then we can write alternative identities using the rules of equation. We've seen this already. For example, we know that cosine squared theta plus sine squared theta equals 1. And we have been able to now solve for sine squared by subtracting cosine squared from each side. That's allowed now that we know that the first is truly an identity. We've also seen where we can divide each side, for example, by cosine squared theta and create a new identity. Okay, so let's take a look at some examples. For each of these, we're going to demonstrate or prove or verify that the equation actually is an identity by transforming the left side to be equivalent to the right side. So we'll demonstrate or prove or verify that the left side is equivalent to the right side. And we know that secant theta is 1 over cosine theta, and cotangent is cosine theta over sine theta. We kind of take a look at what we have and analyze, and we see, oh, the cosine theta, they will divide out, and we're left with 1 over sine theta. And this is equivalent to cosecant theta. And that's what we're hoping to get, cosecant theta. We can see it on the right side. Now notice that we showed all of our work on the left side. We didn't write anything on the right side because it wasn't ever going to change. We just needed to show that the left side is equivalent to the right side. Now at the end of a proof, I typically put QED. This is not required, but that's how I end my proofs. It's a Latin phrase, it stands for a Latin phrase anyway, which is quod erat demonstrandum. And basically that means that which was to be demonstrated. QED. We can also say, ta-da, or done. As I mentioned, not required. Or at least ask your instructor whether it is or not. Okay, here's example B. Again, to verify these proofs, to demonstrate, we're to simplify the left side. And we kind of think of the right side as the prize, the thing that we're trying to get to. The prize. Keep your eyes on the prize. So cosecant theta is 1 over sine theta, all divided by cotangent, which is cosine over sine. The way we're going to simplify this is to treat it as one fraction divided by another, which means times the reciprocal of the denominator. And fortunately, the signs divide out. We get 1 over cosine theta, and that is equivalent to secant theta. That's the prize. That's what we wanted. So we know that we have done our proof, our verify correctly, QED. Yay, me! Okay, our next example, we have a plus sign on the left side. That's kind of interesting, and yet only 1 on the right side. I wonder what that's all about. Well, let's find out. Cosine x over secant means cosine over 1 over cosine x plus sine x on top, all divided by 1 over sine x. Okay, we have a complex fraction. In each case, what we're going to do is multiply cosine x, treat that as over 1, over the denominator reciprocal, cosine x over 1, plus sine x over 1 times the denominator reciprocal, which is, well, sine x over 1. Interesting. So that gives us cosine squared x plus sine squared x. Oh, that's equal to 1. Very cool. QED. Now, I don't know if you noticed that this time the argument is x. Normally, we've been using theta for the argument of each trig function, but this time it's x. That doesn't matter. It's still legitimate proof, still a legitimate identity. Okay, so let's see what we've got here. Oh, yeah, you know something, when we have something with cosine squared or something squared, it might be Pythagorean. We'll see how that fits in. Again, notice on the left side we have a minus sign. So let's see what happens with that. Secant is 1 over cosine. Cotangent is cosine over sine minus sine theta, just as it is, over 1. And when we go to simplify this, let's see, in the first pair of fractions, see cosine theta can divide out. We get 1 over sine theta minus sine theta. The question is, should we, we get a common denominator here. That's right. And the common denominator, I think you can see it already, is sine theta. So that means that we need to make the second fraction have that denominator by multiplying it by sine theta over sine theta. So let's see what we get out of this. We have a common denominator of sine theta, so that becomes a single fraction. And the numerator is 1 minus sine squared theta. There's the Pythagorean. That's an identity. 1 minus sine squared theta is cosine squared theta. So cosine squared theta over sine theta, and that is the prize. That's the prize we were waiting for, cosine squared theta over sine theta, QED. Yes, Let's see what's next. Okay, this time cosine x times the quantity cosecant x plus tangent x. We're going to go ahead and distribute the cosine x through to each one. And from that we get cosine x times cosecant x, just as it is. We're not doing any simplifying that way yet. We'll get that in a moment. Plus cosine x times tangent x. Now we're ready to rewrite cosecant x as 1 over sine x. So you can see we have cosine over 1 times 1 over sine x plus cosine x, again, over 1, times tangent x, which is sine x, over cosine x. Not exactly sure where it is that we're going to go with this. Let's see, we get cosine x over sine x. Right, and on the second one, the cosines divide out. Okay, I'm good with that. So we get sine x still over 1. Where is this? Are we going to get common denominators this time? Oh, what's this? Oh, yeah. Keep your eyes on the prize. Cotangent x plus sine x, we're actually just about there. When we realize what we're supposed to do, what we're supposed to get from this, we don't need to get common denominators. We already have it. Cotangent x plus sine x. So it's equal to cotangent x plus sine x and QED. All right, next. Verify cotangent x times sine x plus secant x times cosine squared x. Well, let's just go ahead and get started. Cotangent is cosine over sine times sine x over 1 plus 1 over cosine x times cosine squared x also over 1. Why did I forget to do that? Oh, there they are. Over 1 over 1. Let's see how these simplify. I'm not sure where to go with this just yet, but we kind of play it out and see where it takes us. Sines cancel in the first two fractions, and a cosine x cancels in the second set of fractions. So we get cosine x plus cosine. Oh, I see. We have 2 cosine x. Okay, that makes sense. And of course, equals 2 cosine x. QED. Let's see what's next. Verify. Cotangent theta times cosine theta. So we have a single term on the left, but a minus sign on the right. So it suggests that, oh, we're going to have a Pythagorean identity in here somewhere. It will appear somewhere. Let's wait and see. So cotangent is cosine over sine and times cosine theta over 1. Okay, let's see. Here it comes. Cosine squared theta over sine theta. Anytime you have something squared, Pythagorean identity is not far behind. Not always, but oftentimes. Yeah, so this is how it is that we make one term into 2 terms, is Pythagorean identity. And that means that we do have to have something squared. Okay, so let's remember what the cosine squared theta identity is. It is 1 minus sine squared theta over sine theta. And we've got 2 terms. Well, this is when we're going to separate the fraction now. 1 over sine theta minus sine squared theta over sine theta. Keeping our eye on the prize, that is going to be what we need, the cosecant theta and minus sine theta when we divide that sine theta out. Great. Cosecant theta minus sine theta. QED. Crazy, man. All right. So let's see what's next. Verify, prove, demonstrate. I'm not sure where this one is going, but we might have Pythagorean again, because we're going from 2 terms down to a single term. So, on the second pair of fractions when we multiply, that becomes sine squared theta over cosine theta. And fortunately, we already have common denominators. So we can combine this into a single fraction, 1 minus sine squared theta over cosine theta. And that is Pythagorean. That's cosine squared theta over cosine theta, which simplifies quite nicely to just cosine theta. Okay, QED. And that means, yay us. Well, I hope this has been helpful to you. I'll see you next time. Bye-bye.